Welcome back, everyone. So the title of this talk is Connecting Models and Data. As you might guess from the title, I will be talking about models and data. Let's see. Nope, that's not what I want. Here we go. Okay, so quickly, as we dive in this week, the first session for many of you, there's an important fundamental truth that you must understand about the DSFP. And that truth is that statistics is an entire field. Statistics is not a day. It's not 3 days. And sadly, for all of us, it is not 5 days. Right? Nevertheless, we are going to try to cover as much as we possibly can in the course of this week. Okay? Even though that is impossible. Some might say a fool's errand. The reason why statistics is important for all of you that work in astro areas is that our field is driven by observations. Right? And so we're going to narrow the scope slightly from all of statistics to instead really focus moving forward on data. Again, this is what drives astronomy, and models. Models are how we understand the universe after collecting our data. So this leads to one of my favorite questions. I love asking this. Some of you have probably heard this before, but what is data? I want you to take a second to think about this. What is data? Would anyone like to share with the group? What is data? Daniel? Any observed quantity. Okay, great. Other ideas? Maria? Systemically collected information. Great. Anything else? Signals. Carlos? Yeah. Signals. Say that one more time. Signals. Yes, great. All of these are wonderful ideas. Yes. Okay. So there's a lot of philosophical ways that we could answer this question, going in directions beyond what we've already discussed. Right? But I'm going to say that for our purposes this week, data are measurements. Right? For our purposes in astronomy, data are measurements. And the thing I want to impress upon all of you is that measurements are constant. Your data are constant. And this may be a new idea. You maybe have heard people say data vary or data change, right? Data do not change, okay? Before I jump into that idea, I want to also note that all measurements come with uncertainties, okay? This is fundamental. You cannot know anything perfectly, right? Heisenberg. So if you are going to perform an analysis on some measurements that you are making, that analysis should take into and incorporate the uncertainties on those measurements that you have made. Okay. Another question, what is a model? Spend a second or two thinking about this. Any thoughts? Kidus? So a model can be a way to extract structure from data. Great. Ulas, yes? Great.
It's like an approximation for a system.
An approximation for a system. That's a great idea. Yes? Okay, Yogi? A model can be an attempt to understand where the data are coming from. Yes, I'm loving all of these answers. Great job, everyone. So models are constructed to explain data. And we generally use models for two different purposes. One is to forecast. So maybe you've, to go back to an example from earlier, rolled a fair die 7 times, and you want to understand, if I roll this again, what is the probability that I'm going to get a 5, right? This is forecasting. But models are also importantly and critically used for inference. This is understanding, right? What is driving what's actually happening in the observations that we obtain. So if, for example, you want to understand what is the mass of the black hole at the center of some galaxy somewhere out in the universe, forecasting is incredibly useful. We have something called the M sigma relation. You can take a spectrum of that galaxy. You can look at the velocity dispersion of the stars in the core, and now you have a sense of what is the mass of the black hole at the center of that galaxy. What you do not have from the M sigma relation is any idea for why it is the case that stars that are well outside the sphere of influence of the central supermassive black hole are actually orbiting faster when the black hole also happens to be larger. Right? That is inference. Okay, so inference is about getting at the fundamental relationship between the parameters that we're studying and between the things that we may be forecasting, right? So forecasting doesn't guarantee you inference, but inference allows you to forecast. Inference is why we are here. This is why we are pursuing astronomy. We want to understand the physics of the cosmos. We want to know why things are the way they are, and we learn that from inference, right? Okay. So it's very useful to say conduct an experiment and collect measurements or data by looking at what happens if you push a ball. And then you can do this 10 times. And maybe after you've repeated this measurement several times, you can say, okay, if I apply some new force F nu, that's going to accelerate the ball by an amount F nu divided by the mass of the ball. That's useful, right? But that's nowhere near as powerful as being able to say force equals mass plus acceleration times. Force equals mass times acceleration. No one do a unit analysis on me for that one. Okay. All right. Force equals mass times acceleration, right? This is universal. Yes, of course, it breaks down in a lot of different circumstances, but this is universal, right? This is not just a ball with a specific force applied to it. This is any object that you can find. Force is mass times acceleration. Okay. So for the rest of the lecture, I'm going to be focusing on building models. And a lot of what you'll be learning about over the course of this week is building models. And there's many different ways that you can construct a model and then interpret the results from a specific model. And that is a lot of what we'll be doing today. Right? And learning how we can do this, again, to get at inference, to understand what is the physics, what is the underlying physics that drives the things that we observe in the universe. All right, so first problem, let's talk about some basics for how we can build a model. I want you to consider the following data. I want you to chat with the person sitting next to you, right? What can you infer from these data? And I'll click back to the graph in a second. Let's spend like 30, maybe 60 seconds on this. What can you infer about these data? All right, let's wrap up in the next few seconds. All right, let's wrap up our conversations, please. All right, thank you. All right, the question was, what can you infer about these data? I asked you to discuss this with your partner. Typically, I would now ask you to share, but I played a tiny bit of a trick on all of you. I'm sorry. Please don't hate me forever. But what can you infer about these data? Essentially nothing. I just plotted a bunch of dots. And I called it X and I called it Y, right? But what can you infer? Well, what is X? What is Y? If these are data, i.e. measurements, how were those measurements collected, right? If we want to perform inference, these are all things that we need to understand. Okay. All right. So let's sweep all that under the rug, and let's just assume for that data that I sent, that I plotted up there for all of you, let's suppose that there is some underlying relationship. X and Y are connected somehow. Okay. So we can construct a model to try and explain this data. All right. What is the best fit model explaining the relationship between X and Y? I want you to discuss this with your partner. This one's not a trick. Okay. I promise I only get one of those per session. So what is the best fit model explaining the relationship between X and Y? You want to see the plot again? I'll put the plot back up. All right, let's wrap up in the next few seconds. All right, so let's share a little bit. What is the best fit model between X and Y? Kai?
We guessed linear, but we said that we really couldn't say for certain either or because there's not a lot of like points populated in the like high X region.
Okay, so possibly there's a linear relationship. And to be clear, you mean a line, basically a polynomial first degree when you say linear. Okay, great. Tricia.
Reveal a polynomial of very high degree that would possibly feed all the data.
Okay.
Maybe something like very other like new data.
Okay, so maybe there's a very high degree polynomial that actually describes the relationship between these particular observations. Okay, great. Anyone else? Okay. I want to unpack this idea a lot. In fact, this is going to be a lot of what we talk about today. What does it mean to be a best fit model? What is a best fit model? All right. So, and we're going to take a little journey starting from like very, very beginner statistics, i.e. not real statistics, and sort of build up towards talking about the frequentist approach to problems like this. So when I was very first taught, I'm going to put it in air quotes, statistics, I was told that if you run some experiment, and again, this is like a, in a classroom, a lab where you have a ball, you apply a force, and then you try to figure out what's the acceleration, right? I was told, okay, plot all of the data and, oh, sure. What is the Zoom question? Yeah.
Ruby says, is it not important to distinguish between the best fit model in a mathematical sense and a physical sense, the latter informing our priors of goodness?
Okay, so we have a question with a whole bunch of technical terms, some of which we haven't defined yet, but the question was, is there a distinction between best fit in terms of a mathematical, or I'm gonna change the phrase slightly, statistical sense versus something that actually gives us physical insight? I'm gonna slightly punt on the question simply because this is what we'll be answering over the course of the lecture today. But there are different definitions that one can use for best fit, certainly, and we're going to get into that over the next several slides. Okay, so as I was saying, when I was first taught, I was taught guess and check. Put your data on a plot, guess what you think the slope is, guess what you think the intercept is, make the plot and see if it looks okay. All right, so let's do this, right? This is kind of the very first thing you could do, and this is not too different from right? Just being like, here's a bunch of X and Y's and tell me what's going on, right? This is not too different from that if you don't have anything else. So here's a guess that I made. Is this best fit? I see mostly shrugs. One person said most definitely. Okay, I love the confidence. But this is guess, right? I mean, like quite literally, there is no foundation for what this is. And if we all did this, none of us would get the same answer. That's probably not good when we want science to be reproducible. Okay. All right, so not best fit. Numerical measures, right, should be used to estimate what is best. So statistical methods should be used to estimate what is best. So what can we do? What other procedures can we follow? So one thing to do would be to say, okay, I do think that it is a line, a first order polynomial that describes, that is basically the model that describes how these data were generated. And so I'm going to minimize for all of my individual observations the distance between the individual points and the line over all of the observations. I'm going to take the sum of the difference between the line and all of the points along the y-axis. I want to minimize that. This is called the L1 norm, or making the absolute values as small as possible. Absolute values of the residuals as small as possible. Okay, and so that looks like this. Clearly, we have now found the best fit. We use math, and math is never wrong. Okay, well, but why did we pick the absolute value? Probably at some point in your life, you've been told that really what you want to minimize is the sum of the squares of the residuals. This is called the L2 norm. Let's see what that looks like. Now we have the best fit. Lecture over. I hope you enjoy the notebook. Okay, so is this better than the guess? Probably. Is this the best fit? Is this the best fit model? A lot of textbooks would tell you yes, right? But why did we pick residuals squared? Like 2 is such a small number. Why would you use such a small number? What if we used a big number? What if we did the residuals to the 100th power? Is that the best fit? Okay. Nice. We did it. I think we solved the best fit for these data. It is without question that thick green line. Okay. All right. So I just realized something. I told you at the beginning, you have to remember the uncertainties. I totally forgot about the uncertainties. So all of those are worst fit. Definitely not best fit. Okay? We need to incorporate the uncertainties. Well, what if we take the square of the residuals and we normalize those by the uncertainties? This is sometimes called the chi-squared. And you maybe have heard this term before when it comes to model fitting. You want to take the sum of the square of the residuals divided by the uncertainties squared on the individual observations, or we're going to normalize the residuals by the uncertainties, right? Essentially, what you're doing in this scenario is you're saying, if I have some observation with a very large uncertainty, I'm going to give that observation less weight, right? If I measure 12 plus or minus 9, I don't have a lot of confidence in that measurement, so maybe that shouldn't influence what I think is true for my model. Okay, so if I minimize the chi-squared, I get the following. This is a little bit like hard to follow at this point, but still we can ask which of these is the best fit? Which one is the best fit? Okay. So the actual true relation, which you will never know, but I do in this case because all of this is fake. I'm the one who made it up. It's in a cell at the very bottom of this notebook. You can go do it yourself. Okay. The true relation is that green line, which looks nothing like any of our best fits. What do we make of this? I want you to chew on that for a little bit. Okay, so again, which is best? And the reason I like asking this question is that it's hard to get to the end of a paper that has data and has fit a model without at some point the phrase best fit model showing up within the paper. And so this is an idea that I just want you to think about. What does that actually mean? And has the procedure that's been implemented in the paper actually done something that I consider to be the best fit? Or are they just saying best fit with some math behind it? To go back to Covey's question from just a little bit ago, right? So are we just doing math, or are we trying to actually figure out what's going on in the cosmos, right? And let me also ask, do we ever know the true relationship in nature? Okay. In this session and throughout the DSFP, you will find yourself fitting lines, much like the data I was showing just a little bit ago. We will be fitting lines a lot. But do we ever truly, truly, truly know, as we've collected our measurements, that y equals mx plus b? I want you to chew on that a little bit too. So now I want to get into the statistics a little bit, right? And start to define some terms that you've actually seen already, but we didn't use these words before. And I'm going to start by talking about the likelihood. So building on this morning's lecture, you can use probability theory to build a notion of what is best, of how you perform the best in terms of selecting a model. So if our observations follow some known or assumed behavior, and the default, if you otherwise don't know, is that we assume that the uncertainties are Gaussian. Okay, so if we make this assumption, we can write down the probability of any individual observation as a function of the model M, and it's going to depend upon the model parameters theta. So for the line that we had a second ago, those model parameters are M and B, slope and intercept. Okay, so P of X, the observations given the model and its parameters. Okay. So when we assume that things are Gaussian, then the probability of any individual observation is described by the Gaussian distribution, which I've written up here. And for some reason, the square root is broken. I don't know why. All right. But here, mu is the mean. And this is the mean of the model. This doesn't have to be a single number. If you had some complex 17th order polynomial, mu is the value of that polynomial at x, right, divided by the variance, or sigma squared. So this is the probability of any given observation that you might have. If all of your observations are independent, meaning that if you make one measurement and then you make the second measurement, and the second measurement doesn't strictly depend upon the previous measurement. So if we're looking at velocity dispersions in the center of galaxies, if I look at a galaxy over here, there's no way that that observation is going to affect what I see in a galaxy over here, right? So we have two independent measurements. We can define the likelihood, L, often script L, I think it's not rendering quite right on the screen, sorry, of all of the individual observations, x sub I, as being the product of the probability of each of those individual observations. Okay. And the likelihood is often how we go about figuring out what are our best fit model parameters. It's a question, Jordan. Why it's a product? Because it's, so the likelihood, I think I say this on my next slide. So the likelihood, this is a great question. So the likelihood is not a probability. So this is an important thing to remember. It is essentially asking, if I multiply a whole bunch of probabilities together, how likely is this particular outcome? Okay. So it's not itself a probability. It does not integrate to one. And in fact, it's almost always a very small number because you're multiplying a whole bunch of probabilities, which themselves are less than one, together, right? A whole bunch of small numbers multiplied together will be a very, very small number. All right. For the special case that you're working with a Gaussian, the likelihood can then be written as a product of a whole bunch of Gaussians. I'm not going to read everything off of the screen, but we're just multiplying all of these Gaussians together, where sigma sub I is the uncertainty on the individual observations. If every observation has a different uncertainty, this is called heteroscedastic uncertainties, meaning they are not all the same, right? For your individual observations x sub I. All right. The likelihood is normally very, very small. And so typically, we are dealing with measuring things or estimating likelihoods on computers, and we'll work with the log of the likelihood. so that we can actually find that the numbers are tractable on our computing systems. And if you take the log of a product, you can turn that into a sum, as is shown by the equation above me right now. Okay. And the first two terms in this equation are constant. If you have collected 100 measurements, n equals 100. Okay. And whatever the uncertainties are on those measurements, those uncertainties do not change. So if you change your model parameters, right, those first two terms, they do not vary at all. And so this allows us to write that the log of the likelihood is equal to the sum over all observations of the difference between the observation, the mean value squared, divided by 2 times the uncertainty on the individual observation squared. Okay, this is the log likelihood. Aritra.
So each one of those are for, each one of the Gaussians are for each parameter.
The Gaussians describe the observations themselves. So the observations have a Gaussian uncertainty, but the parameters of your model are what define the mean mu. So in the simple example that we've been referring to, which is fitting a line, then mu is set by the slope and the intercept. Mu is not constant. Mu changes depending upon where you have observed. So to use my galaxy example, mu will be different, right? Mu is your expectation from the model. So it's the slope multiplied by x, or let's say for the m sigma relation, multiplied by the velocity dispersion plus the intercept b. If I measure a velocity dispersion of 100, mx plus b will be different than if I measure a velocity dispersion of 250. Then I'll have m times 250 plus b. Okay, sorry. So yes, mu could be indexed by I, and that would probably make this a little more clear. That's a great point. Yeah, yeah. Maria.
Like problem set maybe working on right before this,
Mm-hmm.
it was mentioned that two transformations, like some properties don't carry across, and I'm wondering how that would apply in this scenario because you're taking the log of the likelihood.
Yeah, so that's taking the log of specifically a distribution. The likelihood is a number, so it's just a whole bunch of probabilities that are multiplied by each other. So the log of the likelihood is just the log of a number, and you can transfer back and forth between the likelihood and the log of the likelihood just by a simple mathematical operation. Okay, all right. So I'm now going to argue, after saying what does it mean to be best, I'm going to argue that the best model is the one that maximizes the likelihood. Or another way of saying this is, can I select model parameters that essentially make it most probable, most likely that the observations that I have are the observations that I would obtain if I were to collect 100 measurements or 1,000 measurements or 1,000,000 measurements, okay? So if I have some observations that are fixed and unchanging, right, we're looking for the model parameters that produce a model that maximizes the likelihood. And so we have a model now that, quote, best explains the data. All right, so I want to talk about looking at this from a frequentist standpoint, and this will be a little bit different than the lecture you have after this afternoon's break. As we already mentioned, there are two differences to the modern ways in which people approach statistics. One is frequentist and one is Bayesian. A lot of astronomers will tell you that one is better. I am not here to tell you this today. I'm just here to tell you that there are two different ways that you can approach this. Okay, neither of them is wrong, right? And I want to emphasize, as a big picture idea for the DSFP, that what you should be endeavoring to learn as a data scientist that works on astro, is what types of problems exist and what is the optimal solution for the problem at hand. And there are lots of problems in astronomy where a frequentist approach is smart and the correct thing to do, I would argue. And there are other problems where a Bayesian approach is smart and the correct thing to do. And so I do think you need to be familiar with and understand both, even though if you look at what the lectures are this week, the lion's share of the time is going to Bayesian probability theory. Okay. All right. There are three tenets of frequentist statistics. Okay. One is that probabilities are frequencies of events. Or in other words, one way to understand probability is to repeat your measurements an infinite number of times. And what results do you get as you repeat these measurements an infinite number of times? So that's what it means to be a probability. If I flip a coin literally infinity times, how often does it come up heads? Another important tenet is that the parameters are fixed, unknown constants. This means the mass of the electron is the mass of the electron. There is a number that none of us know, but there is a number that is the absolute and correct mass of the electron. However many decimal places you need to go, there is a number, and it's fixed. It does not vary. This is an important tenet of frequentist statistics. It's different in the Bayesian regime. And then, as I said a second ago, statistical procedures should have well-defined long-run frequency properties. So as you run experiments again and again and again, right, you should approach limits that are well understood. So these are the tenets. Okay. So let's talk about how we actually then take this likelihood and turn it into an estimate of model parameters. So first and foremost, you do have to come up with a model. You have to say, this is how I think the data were generated. Earlier, we had an idea for a high-order polynomial for the data set we looked at. We also had an idea for just a first-order polynomial, a line. Okay? The model parameters that maximize the likelihood, that is your best estimate for those parameters. Okay? In some cases, this is actually very straightforward. For a line, or if you want, for any polynomial, you can actually just write down a relatively straightforward analytic solution and get the answer. It's a little bit of matrix multiplication. It's not that bad. But in many cases, there's not an analytically tractable solution, right? And so we use numerical methods. And this is what we'll spend time working on in the notebook. Now, it turns out that maximizing the likelihood is equivalent to minimizing the negative log likelihood. And this is what we ultimately do in practice. Okay? We try to minimize the negative log likelihood. And we do this using the minimize function in SciPy optimize. Right. A caveat that's important about using numerical methods to try to find best fit parameters. You never have a guarantee that you will have found the global minimum to the function that you have, right? So roughly speaking, the way numerical solvers work is that if you're at some location in a multidimensional parameter space, you essentially ask, in which direction in this multidimensional space can I go with the most negative slope? And then you go in exactly that direction, and you ask the question again, where can I go? And you follow this path. And eventually, the slopes start to decrease, and you hit a little minimum. But there's no guarantee that that's the global minimum. So it's important to remember this, particularly if you're using numerical methods to solve for model parameters and putting your results in papers. Okay? Now, I'm saying that this is true of frequentist methods. This is also true of Bayesian methods, right? There's unfortunately no way out of this particular problem. We can come back to that later. All right. If you have a Gaussian likelihood, which is what we've been focusing on so far, you can recast your likelihood in terms of the z-score, which again, this is just your normalized residual, x sub I minus mu over your uncertainty. And so your log likelihood is equal to some constant minus 1/2 the sum of your z-scores squared. And this is often referred to as chi-squared. So in a lot of papers, it is stated we minimized the chi-squared. That equivalently means we maximized the likelihood. Why is this called chi-squared? Right? Well, it means that the distribution that you have for the log likelihood is actually determined from a chi-squared distribution, which is a specific mathematical distribution that has n, the number of observations, minus k, the number of model parameters, degrees of freedom. Okay. I.e. the probability, right, that you get the chi-squared value that you observe or measure is described by a PDF. Okay. Wait. Okay, no, I don't want that. This is what I wanted to show really quickly, okay? So this is the probability distribution that describes the chi-squared value that you have, right? As you have more observations, the probability of Q becomes larger. The mean of this distribution is the number of observations that you have, the number of degrees of freedom that you have. Okay. We'll come back to this in a second, but you can use the chi-square distribution to get a sense of how good is your model based on the chi-squared score that you have measured. All right. So we had this notion of, well, maybe this is not actually a line in the data. Maybe this is some weird complex polynomial. And indeed, it turns out that you can lower the, you can improve the likelihood, you can maximize your likelihood by adding additional parameters to your model. There's 20 points in the graph that I showed you earlier. If we use a 19th order polynomial, we can have a model or a line that perfectly goes through all of those data points. Okay. Is this best fit? Is this better? Having the sum of residuals equal to 0. We also heard that maybe if we do this, we'll be overfitting, right? So it's useful in this sense then to be able to define the chi-squared per degree of freedom, because going back to our plot here, right? The mean of our distribution is equal to the number of degrees of freedom. We expect a higher chi-squared when there are more degrees of freedom. We expect a lower value for chi-square when there are a lot of degrees of freedom. And typically, if you have found that you have a model that has a chi-squared per degree of freedom that is much, much greater than 1, either your model is underfit relative to the data, or it is also possible that you have significantly underestimated the uncertainties. This is a big, big challenge in astronomy. Okay? Alternatively, if you have a model where the chi-squared per degree of freedom is much, much less than 1, you've either overfit substantially, or you have overestimated your uncertainties. Okay. So generally speaking, if we have a chi-squared per degree of freedom that's about 1, we would call these models good. But this in and of itself is not sufficient. We do need to pay attention to how many degrees of freedom that we have. Okay. All right. So one way, if you're considering different models, and we're asking about best fits, and we're asking about what is the optimal physical understanding for what we've derived, one way that we can do this is by comparing models based on their chi-squared. The problem with strictly using only chi-squared is that the penalty tends to be too small for adding new parameters to the model. So there are other ways that we can compare models. The Akaike information criterion, or the AIC, is one of these ways that's often used in frequentist statistics. Right? So just very quickly, the AIC is calculated as -2 log L plus 2k plus 2k k plus 1 over n minus k minus 1. So these extra terms beyond the likelihood, right, are increasing the penalty. They're saying that there's a penalty if we go from 2 model parameters, m and b, to a 19th order polynomial, right? We're adding a greater penalty to the AIC, and models with the smallest AIC are preferred. There's another measure called the Bayesian information criterion, which I'm just going to say right now, but that's not part of the slides, but it's similar idea. You can measure the likelihood, and then you add a penalty as you increase the overall number of terms. Right? And so if 2 models have the same likelihood, the model with the smallest number of parameters wins. I would intuitively say this makes sense. Right? Simplistic models are preferred to more complex ones unless the simplistic models cannot explain the observations that you have. So this is a quick notion for one way in which we might be able to compare some models. As I said at the start, I was hoping to connect models to data for all of you. And whether you decide that you like to be a frequentist or you like to be a Bayesian, either way, you are going to find the likelihood to be vitally important. So if you take nothing else away from this talk, right, likelihood is important. Okay, that's the thing to remember. We also talked a bit about model comparison, which one's best, how do we figure out what is best, right? And I want to end with a question that might bother you, which is, what is the probability that some selected model, right? What is the probability of some model given an infinite set of models? So y equals ms plus b, what is the probability of that, given that there's an infinite number of models out there that might explain the data? Okay. You can't do this. You can't know it. There is no way to answer this, right? No single model can ever definitively be declared to be correct. Newton was the best for 200 years. And then we got new observations, and we had to come up with a new way to understand gravity. You can never know this for certain. That the model you've written down and you fit parameters for in your paper is in fact the correct model. So now that we've spent a bunch of time working on probability and statistics, we're not going to do a notebook. We're just going to go up the river and play some games at the casino. All right. That's all I have before we jump into the problems, but I'd love to take any questions if there's further questions. Yes.
I understand that there's nothing that can definitively be shown to be correct, but I'm pretty sure me and my advisor are going to have a meeting at some point where I'll have to defend my whatever model of fit that I have. What are the best practices to make sure my fit is at least something that would be respected by someone who's scientific?
Okay, so this is a great question. Indeed, I ended with a bit of a downer. I think this is a fun thing to think about, but I don't think this is something that I worry about in the following sense. We can never prove it. Right? We can never prove it. And so I think the standard, as we've learned over many centuries of developing the scientific method, is that we build a model and the proof comes in the ability of the model to explain new observations. So if you are walking into your advisor's office and you say, I think this is the model that explains the data, right? You'll have some observations. You'll probably plot some line or some other thing that goes through the observations, and that'll be somewhat of a test. But at some point, someone is going to replicate your observations, often with an even larger data set. Right? This is one of the grand things about astronomy right now. You found you have found 3 transiting exoplanets. Kepler's now found 200. Oh, Kepler, you think you're so fancy. Tess has found 2,000. Oh, Tess, you think you're so fancy. Plato's going to find, I don't know if Plato's going to find more, but this is how things go, right? We're always finding more things. We are able to test our theories. If you say that here is the relation, the M sigma relation, here is the line that describes this, people are going to go out and they're going to go and get more black hole mass measurements. And we now have enough black hole mass measurements, but there's a lot that look like, maybe they don't really fall on that line in the way that we thought they did about a decade ago, right? So it's all part of the scientific cycle. And I don't think you have to worry too much that your model is totally wrong, because if it is, we'll get more data and we'll figure out a better one. Other questions? Yes.
Can you go back to the AIC?
Yes.
If this is something where the smallest one is just the best, why is there a factor of 2 in all the terms?
So I'm not going to remember the answer to that exactly right off the top of my head. I'll look it up and I'll write it. But the motivation behind adding these terms does come from some mathematical manipulation. It's not just made up, let's just throw in a K and let's throw in these other terms here. But I don't remember the history for exactly why this particular equation was landed on. I will say that typically in the literature, the AIC is becoming less preferred. I have it here in the notes for completeness. You will see it in lots of papers where they say this is the model we're selecting as the optimal model because it has the lowest AIC. But I do believe that there are better methods for model comparison, which we'll be covering over the next few days. Okay, all right. I had a Nane first and then Hanye.
Oh, just to answer the previous
Yes.
question, I just took a statistics and machine learning
Okay.
class this semester. So the AIC and BIC models were just, I guess, an evolution of logistic regression
Mhm.
and minimizing the maximum mean discrepancy or the minimizing the likelihood function. They are falling out of favor though now because of just an evolution in how we do our calculations. So for example, in image analysis, if you want to do minimizing functions or something like that, you probably use the evidence lower bound function, which is the ELBO function, or the MMD function, which is the maximum mean discrepancy function. So it's just at one point they were really good indicators for minimization, but there's better models with better optimization. That's how the variables change.
Thank you. Hanye, do you have a question?
Just out of curiosity, if the approach is the same to find the minimum or the maximum, why do we find the minimum minus log n instead of just find the maximum log n?
Again, this gets into history. There is a reason that is currently escaping me because I'm at the end of the lecture. Brian, do you recall why we typically minimize as opposed to maximize? Yeah. Yeah. It doesn't sound like it should be different, but it's just a little bit easier computationally. Yeah. Jordan?
Is there a way to know what your overall parameter space looks like in terms of avoiding the full minimum?
So the question is there a way to know what your multidimensional parameter space looks like in order to avoid local minima? We'll talk about one procedure tomorrow that can help with this, but the only guarantee that any procedure works in this way is if you're willing to wait an infinite amount of time. Okay. But in some instances, you can use reasonable analytic approximations and have a pretty good sense that you may be in a global minimum. But it is hard to provide definitive guarantees that this is the case. Okay, Aritra? The distribution, the plot?
Where you define the chi-square based on the assumption that you're using Gaussian.
Okay, yes. This one, sorry.
So the assumption is that they all follow Gaussian distribution. Right? If there is one parameter that we know based on previous, that does not.
So we're not saying that the parameters are Gaussian. We're saying that the uncertainties on the individual observations are Gaussian.
Right.
Those are slightly different things.
They have prior knowledge that one of the uncertainties do not follow, let's say, Gaussian. When
Okay.
When you're writing down the likelihood function,
Mm-hmm.
it will be the product of the periods, right?
Yes.
And one of them, let's say, is not Gaussian.
Yes.
In that case, we have to derive the chi-square, right? Yeah.
So if if you have uncertainties that are not described by the Gaussian distribution, then you will not have a likelihood that is chi-square distributed. And so all of this math that we went through essentially doesn't become useful any longer. Okay.
But can we find something like a chi-square for that distribution?
You can still maximize your likelihood, right? So you still have all of those probabilities that you can multiply together, and you can choose model parameters that give you the largest value of the likelihood possible.
Does that become false?
Correct, that's right. In that instance, it would not be correct to call it chi-squared because you are not dealing with something that follows a chi-square distribution. Yes. Okay. Jasmine.
Like Japanese versus error estimation.
Okay.
Better. But I've always been kind of like wary about that because you're making an assumption about the points that you're replacing.
Okay, so the question was, can we, I'm going to rephrase slightly if that's okay. You tell me if I'm doing this incorrectly, but can we come up with a method for trying to estimate the uncertainty on our model parameters? And one possible way to do this is with the bootstrap method. There is actually a problem in the notebook that you're about to do on the bootstrap method, but very quickly, the idea is because along the same lines of the very last question I asked in this lecture, we never truly know the underlying probability density function. We don't know the PDF, right? The true PDF for the data that we are observing. And so what the bootstrap method tenets is that your best estimate of the PDF is the observations themselves because they've come from the true underlying PDF. And so a bootstrap method is, okay, well, let me randomly select from my observations to create a new data set where I can make a measure of my model parameter. And then I can repeat this many, many, many times and get some sense on what is the width of the distribution that I get from this bootstrap. Okay. So that's roughly what the bootstrap method is. And I would tell you that if you are working in a frequentist regime, I think that a bootstrap method is an excellent way to get a handle on what are the bounds, or what is the very specifically the confidence interval on the parameter, the model parameters that you care about. Did I answer your question? Okay, we can talk more during the break. All right, there's okay. This will be the last question with us, and then I will still be here walking around as you work on problems. If there's further questions, I'll continue to answer them then, but I want to make sure everyone has time to work on the notebook. So, yes. Okay.
Let's say working with spectra and you want to fit a model.
Yes.
It's usual that sometimes these spectra are normalized at one data point, where the uncertainty at that point, data point is 0.
Okay.
So when you try to fit a model like this by minimizing chi-square, the denominator goes to 0 because at that point the uncertainty is 0. Are there ways to tackle this problem?
I want to talk a little bit more about normalizing. This might be specific enough that we should talk about this afterwards, but what I am typically familiar with, if you have a spectrum and then say you're normalizing a bunch of spectrum either to each other, or you're normalizing a spectrum so that you have, say, a flat continuum, right? Either of these procedures is typically dividing by a constant, but it's not a procedure that changes the uncertainties on an individual observation to be identically equal to 0. So I want to talk about that a little bit more. But if you had an object, well, put differently, if you go back to the very beginning of the lecture, I said you cannot have an uncertainty that is identically equal to 0. So if that's happening, I think that's a numerical thing that's happening. That's not truly reflective of the measurements that have been made.
So way of defining other data points in the spectrum with respect to one of the data points.
So
when I say normalizing, that's what I mean.
Okay, but if you've measured one quantity, Q, that's some number plus or minus some other number, and then you've measured some other quantity, F, that's also a number plus or minus some other number. If we divide those two things, there is an uncertainty on, there is an uncertainty that propagates on the result of that division. And then if there's 1 point, because it's a spectrum where you divide Q by Q, so that you get 1, you still have an uncertainty on that particular measurement of 1, which is related to what the uncertainty was on the original measurement itself. Okay? So I think there should still be an uncertainty everywhere, but we can talk about that more if I don't quite have that right. All right, so if you haven't already, these slides are in the repo. You can do a git pull. Please start working with your partners. I and the other instructors will be walking around answering your questions, but you'll have a chance to work through some maximum likelihood estimation using numerical methods, where you'll also get uncertainties on your model parameters and do a little model comparison at the very end. Okay.
The notebook that has the problems is called
Maximizing the likelihood, or
maximum.
something very close to that.
Okay.
Yes.
Thank you.
MLE, yes. Thank you, Jordan.